These are fascinating times in mathematics. Chaos, fractals, dynamics, all of these are terms that are very much in the news these days. What I'd like to do today is tell you a little bit about what these terms mean and where they come from. These are terms that come from the area of mathematics known as dynamical systems. I feel that dynamics is a natural topic to expose students to in high school or in college. It's a fascinating area of mathematics. One reason it's so fascinating is because, as you'll see today, the computer graphics images that come out of the field of dynamics are beautiful. There's something in these computer graphics that strikes the human eye as quite alluring. Another reason for the fascination with this field is the fact that it's so exciting. Much of what you'll see today is less than 10 years old. This is new mathematics. One might think then that this area of mathematics would be somewhat esoteric since it's so new, but in fact much of this mathematics is very accessible. We're talking about quadratic functions, sine, cosine, the kinds of things that students in high school know quite a bit about. Finally, this area of mathematics involves in an essential way the use of the computer. Computers, computer graphics, and computer experiments are essential to understanding and working with dynamical systems. Finally, this area of mathematics promises to be quite applicable. Anyone who's read the book by James Gleick called Chaos, The Making of New Science, will see the tremendous power of this mathematics in terms of applications in all areas of science. Let me begin by showing you a videotape of some of the computer graphics images that come out of this research. The film you're about to see is a film about sine and cosine, a film that I've made as part of my own research in dynamical systems. What you're looking at here is a Julia set. This is one of the terms that I'd like to talk about today. Julia sets are one of the most complicated objects in mathematics and also one of the most beautiful. Notice the intricacy of this image as it changes. These images are produced by a process called iteration. We'll talk a lot about what iteration means, how it applies, and in fact how these images are created using the computer. What you're seeing is the scientific topic known as the collapse of a Siegel disk. No one really understands what's happening in these films. In fact, this film was seen for the first time barely 4 years ago. So let's begin by talking about what we mean by a dynamical system. Basically, a dynamical system is any process that moves or changes in time. As such, dynamical systems occur in every branch of science. For example, the motion of the planets in celestial mechanics. There's a good example of a dynamical system, of a process, of something that's evolving in time. The weather, another system that changes quite dramatically in time. Similarly, the stock market, economic systems. These are good examples of very chaotic, at times, dynamical systems. Finally, in chemistry, simple chemical reactions are examples of processes that evolve in time. When a scientist confronts a dynamical system, the question he or she asks is, can I predict what will happen in the future? Can I predict how this motion will evolve in time? Now, as you look at these examples of dynamical systems, you say, well, some of these dynamical systems are clearly predictable. The motion of the planets, for example. You know that tomorrow morning when you wake up, the sun will rise. Similarly, chemical reactions. You know that tomorrow morning when you put cream in your coffee, the resulting chemical reaction won't be an explosion. On the other hand, the weather or the stock market, those are examples of dynamical systems that seem totally unpredictable. If I knew where the stock market would be tomorrow, I wouldn't be here today. I'd probably be on some beach catching the rays. In any event, these are examples of dynamical systems that, unlike the first two, are quite unpredictable. The question is why? You say, I know why the weather and the stock market are unpredictable. Those are dynamical systems that seem to depend on just so many variables that it would be impossible for anyone to know all of the variables at any one time so as to make a prediction. For example, to predict the weather, you would have to know all elements of the weather around the globe instantaneously. You'd have to know the barometric pressure, the wind speed, the wind direction, everywhere on the globe in order to predict what the weather will be like a week hence. Similarly, the stock market. To predict where the stock market will go, theoretically at least, you have to know the behavior of all elements of the economy, of all consumers in the economy. Clearly, these are systems that depend on just too many variables to make a prediction. Well, it's certainly true that the weather and the stock market depend on many, many variables. On the other hand, that's not necessarily the reason it makes these dynamical systems unpredictable. It's one of the most remarkable discoveries of mathematicians in the last 15 or 20 years that very simple systems, very simple dynamical systems, systems that depend on only one variable, not millions of variables like meteorology or the economy, systems that depend on a single variable can behave just as unpredictably, just as turbulently as the weather or the stock market. That's what we'd like to talk about today, how very simple systems can behave in very strange and complicated ways. To simplify the situation, let's begin by talking about a mathematical dynamical system, very simple abstraction of the kinds of dynamical systems that arise in nature. What's a mathematical dynamical system? Well, among the simplest of mathematical dynamical systems are the so-called iterated functions. Start with any mathematical expression, for example, the square root function, and start with any number, say x. How does one create a mathematical dynamical system? Well, through the process of iterating this mathematical function. That's accomplished this way. Take the initial number x, compute its square root. You get a new number. Then compute the square root of that number. You get a second number. And so forth, the square root of the square root of the square root. This is the process of iteration. It's a dynamical system. The numbers are changing in time. The question to the mathematician is, just as in the case of a scientist, can you predict what will happen? Can you predict what will happen when you iterate this function over and over again? Well, now you see that this process is ideally suited for use of a computer. There's nothing a computer can do better than iterate functions over and over again. So to illustrate that, I brought along my own home computer, rather homemade computer. This, you might recognize, something that used to be called a calculator. I call it an iterator. An iterator comes with a bunch of numbers that you can input together with a bunch of functions which you can iterate. This iterator comes with the standard functions, x squared, square root of x, 1 over x, etc., and also with a quadratic function. So this is a fairly special iterator. How does one do the process of iteration? Well, with that square root example, let's start by inputting the favorite number into the calculator. For example, we might input 256. We then iterate the square root function by first pressing the square root button and then computing the square root of 256. That's 16. To iterate, we do it again. Square root of 16 is 4. Square root of 4 is 2. Square root of 2 is 1.41. And then we ask, what happens when we do this over and over again? Square root of 1.41. Keep hitting the square root button. Eventually you'll see that no matter what number you started with, you always end up with the number 1. So here's an example of an iterative process that's completely predictable. No matter what number you start with, when you iterate the square root function, you always end up with the number 1. Here's another example. Let's take the function x squared. Start with any number. Let's say we start with the number 2. When we iterate the squaring function, we get first 4. Square 4, get 16. Square 16, get 256. You can see what happens. Square 256, you get 256 squared, a rather large number. You see that upon iteration, repeated squaring, at least if you start with a number that's larger than 1, tends to infinity. So again, that's an example of an iterative process whose behavior you could predict. Here's another one. Let's take the sine function, the trigonometric sine function. What happens when you iterate the sine function? Well, let's start with any number, say 123, and then iterating. The sine of 123 is minus 0.45 in radians. Sine of that is minus 0.43. Take the sine again, minus 0.41. And you see what happens. Iterating the sine over and over again eventually yields, after 300 or more iterations, the number 0. So if you iterate the sine function, no matter which number you start with, you always end up with 0. Again, a perfectly predictable iterative process. One more example. How about cosine? What happens when you iterate the cosine function? Well, let's see. Let's start with any number, say 123. And what do you think happens when you iterate the cosine function? Anyone know? What happens when you iterate cosine over and over again? Well, it turns out that no matter what number you start with, when you iterate cosine in radians, you always end up with the number 0.73908. Where'd that number come from? Now, we'll talk about that in a minute. But for now, notice that you now know how to iterate, or what the result of the iteration of cosine will be. No matter what number you start with, when you iterate cosine, you always end up with that strange number. One last example. How about iterating the quadratic function 4x times 1 minus x? What happens when we iterate this simple quadratic expression? Well, let's start with any number, say the number 0.4. And what happens when you compute this quadratic expression? Now, if you plug in 0.4 to the quadratic function, you get 0.96. Iterate again, you get 0.154. Iterate again, you get 0.521. Iterate again, you get 0.998. Again, 0.008. Once more, 0.032. See the pattern? Try some more. Iterate again, 0.123. Iterate again, get 0.431. Do it again, get 0.980. Do it again, 0.078. See the pattern yet? Probably not. Iterate again, 0.288. Once more, 0.823. There is no pattern whatsoever when you iterate the quadratic function. That's because this expression is chaotic. That's because this function is totally unpredictable. For all intents and purposes, iterating 4x times 1 minus x is a random number generator. Okay, well, notice that most iterators don't come with a 4x times 1 minus x button, but that's no problem. Most computers do. You could very easily program a computer to iterate a quadratic expression, or in fact any mathematical expression, like 4x times 1 minus x. Here's a simple program to iterate the function 4x times 1 minus x. The program simply asks you to input your favorite number x naught, and then in this loop, we simply compute over and over again the expression 4x times 1 minus x, each time printing the result. After 100 iterations, we stop, and you see the first 100 points computed under iteration of 4x times 1 minus x. At this point, let me introduce some notation that we'll use later. When we iterate the calculator or the computer, that is, when we successively press the buttons on the calculator, we're computing what I call the orbit of the initial point. We start with a number x naught and then press the button on a calculator, we produce a number x1. Press the button again, we produce x2. Press the button again, we produce x3. Successive pushes of these buttons yield the list of numbers that are the so-called orbit of the dynamical system. So the question in mathematics, akin to the question we asked in the beginning, is can you predict the fate of orbits of this dynamical system? Well, now let me interject some mathematics into all of this. Let me show you how you can predict the fate of simple orbits, of simple dynamical systems, by a procedure I call graphical analysis. For example, consider the square root function. I've drawn here the graph of the square root of x, and I've superimposed on this graph, the diagonal line, the line y equals x. How do I use this setup to predict the fate of orbits of the square root of x? It's easy. Suppose I start with a number x and ask for its orbit. Well, to compute the square root of x, what we do is simply draw a vertical line up to the graph of the function. When we reach the graph of the function, the y coordinate of that point is the number, the square root of x. If we now draw a horizontal line over to the diagonal, then we reach the point whose x and y coordinates agree. That is, we reach the point whose x coordinate is the square root of x. So how do we compute the square root of a number? Graphically, it's easy. We simply draw a vertical line to the graph and then a horizontal line back to the diagonal. So how do we iterate the square root function? We do this procedure over and over again. To compute the square root of the square root of x, we simply go to the graph and over to the diagonal. Iterate again. Go to the graph and over to the diagonal. Go to the graph and over to the diagonal. You see by this simple geometric procedure that iteration of the square root function via this staircase method leads you eventually to the point which lies at the intersection of the graph with the diagonal, and of course that's the point 1. No matter what number you start with, if we start out here with an x larger than 1 and go to the graph and over, go to the graph and over, go to the graph and over, inevitably we're led to the number 1. That is, orbits of the square root function always tend to 1, a process that we saw with the iterator a moment ago. A couple more examples. What happens when you iterate the trigonometric sine function? Well, let's see. I've drawn the graph here of sine x. Again, superimpose the diagonal y equals x. And again, let's start with any number whatsoever, say x, and iterate. To iterate, to find the orbit of x, we simply go to the graph and then over to the diagonal, to the graph and back to the diagonal, to the graph and to the diagonal. And again, you see that no matter which x you start with, when you iterate the sine function, inevitably you're led to the number 0. So iteration of the sine gives orbits which always tend to 0. One more example, cosine. Where did that strange number 0.73908 come from? Here's the reason for that number. Here's the graph of cosine. Here's the diagonal. Start with any x, say down here, and iterate by going to the graph and over, 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 to the graph and over. You see that, again, no matter which number x you start with, the orbit of x always tends to the point which lies at the intersection of the graph with the diagonal, and that point just so happens to be 0.73908. So again, there's a dynamical system, a mathematical dynamical system, whose orbits are completely predictable. What about the quadratic function? Well, the quadratic function has graph that looks like this. Here's the graph of 4x times 1 minus x. I've sketched it only between 0 and 1. What happens when you take a typical x between 0 and 1 and iterate? Well, graphical analysis gives the answer by going to the graph and over, 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 etc. You see that the orbits of 4x times 1 minus x bounce randomly around the unit interval, bounce randomly around the interval between 0 and 1. So this is an example of a chaotic dynamical system. The orbits of this simple dynamical system are, for all intents and purposes, unpredictable. So this harkens back to what I said in the beginning of the lecture. Here is a dynamical system that, unlike the weather or unlike the economy, depends on only one variable. Yet, despite the fact that the expression is so simple, the orbits, the dynamics, are completely unpredictable. This is the major discovery in mathematics, or one of the major discoveries in mathematics in the last 15 or 20 years. Now, as a mathematician and a mathematics instructor, can't possibly give a lecture without assigning some homework. So let me ask you to predict the orbits for various quadratic functions. I've listed here a bunch of simple quadratic functions, all of the form a constant times x times 1 minus x, and I ask you to predict the orbits for these functions using either the iterator or the computer or graphical analysis. The first two are easy. 1x times 1 minus x and 2x times 1 minus x. The orbits of these functions, at least for x's between 0 and 1, you'll see always tend to a fixed number. On the other hand, the next two, 3.1x times 1 minus x and 3.4x times 1 minus x, yield slightly surprising behavior. When you iterate this function, 3.1x times 1 minus x, all orbits tend to cycle back and forth between two different values. If you use 3.4 as the value of the parameter and iterate that function, all orbits tend to cycle back and forth between 4 different values of x. This is actually the beginning of what's known as the period doubling route to chaos, another of the very important discoveries in dynamics in the recent decade. Last problem is for you to iterate a constant times x times 1 minus x, where the constant is in the range 3.6 to 4. It turns out that there are very many values of the constant in that range, though by no means all, for which iteration of this function is practically indecipherable. Very few people on Earth know what happens when you iterate a constant times x times 1 minus x, where the constant is in this range. It's a fascinating problem that was only solved by mathematicians in the last 4 or 5 years. So there are some homework problems for you.